The goal of Work Package 4 in Seneca is to develop a set of guidelines for writing portable pipelines for federated genetic data analysis. To share our work, we have a GitHub repository which you can see on the screen right now. It contains all of the code and documentation available to date. The pipelines which we are concerned about are federated, which means that the input information is split across several controlled access human data cohorts. It is often difficult to obtain the permission to export the individual level data from the cohort, and for some national healthcare cohorts it is never possible due to existing regulations. Hence, we developed the approach where exporting the raw data is not necessary. This involves splitting each pipeline into two parts, as demonstrated on this figure. Part A of every pipeline reduces the individual level data to some intermediate summary product, which does not contain personal information. Part A of a pipeline can be run inside the cohort, in theory without ever seeing the data. In Part B, the summary products from all pipeline runs are exported to a central location and then integrated into the final scientific product. Parts A and B are simply individual pipelines written in Nextflow. We chose Nextflow as our main workflow definition language because it is widely adopted and supports a good range of execution environments. There are links to the instructions on how to run a pipeline on different platforms, and below are the links for the actual demonstrator pipelines. Because we are using Nextflow, any pipeline can be run in any environments, which maximizes the portability. The Joint Cohort Genotyping Demonstrator pipeline provides an implementation example for this approach. The goal is to compute some simple metrics, namely allele number and allele count, in a federated manner from two datasets. The datasets in question simulate the scenario with having multiple cohorts. They use different data access protocols, different reference genomes and chromosome name notations, and are processed in two different environments. This is all to demonstrate the flexibility of the approach. Let's go ahead with processing the first part of the input data. We are running this in a CSC Rari cloud using task as an executor. We first log into the cluster, then we clone this repository. Inside it, we go to the subdirectory with the pipeline. Next, we set some parameters for Nextflow to use the test environment. And now we are ready to run the pipeline. While it is running, let's take a look at the parameters. Here we specify the Docker image to run the pipeline with, which contains all the dependencies. And here we have the dataset definition file. Let's take a look. It is a TSV table which for each sample lists its name, the access method, which in this case is FTP, and the URL. The input data which is used in this part consists of 4 BAM files from the Genome in a Bottle project. What we want to do is to genotype a specific region on chromosome 17 and to compile the simple summary statistics, which are allele count and allele number, across this dataset. After some time, the pipeline has completed. Let's look at the results. We can see that the file result.a1.giab was generated in the output directory. Let's peek inside. This is the intermediate level products, importantly not containing the individual genotypes. This file can be exported out of the cohort environment. The second part of the input data is processed on the EMBL EBI LSF cluster. As before, let's start a pipeline first and then discuss the data. Following the instructions, we first log into the cluster. Then we clone the repository, and as before, we go into the right subdirectory. Next, we set the parameters for Nextflow to use LSF as the executor, and now we are ready to run the pipeline. And now, while it's running, let's take a look at the parameters. First, the cluster we are using does not support Docker, so we switch to using Singularity instead. The same Docker image is actually used, but it's being transparently pulled, converted into the Singularity format and cached. Let's take a look at the dataset definition file for this run. The data used here are 4 open access test files from EGA, the European Genome Phenome Archive, and the access method is the EGA Python client, as specified in the fetch mode column. Under the hood, this client is using the HTS-GET protocol to fetch a specific part of the genome from the BEM file. After some time, this pipeline has also completed, and we will see that the file result A2EGA was created in the output directory. Let's take a look. As in the previous run, this is another intermediate level product, which we will also export to the same location. Finally, we are ready to integrate the results. This time, we are running part B of the pipeline locally. Let's take a look at the dataset definition file. The input files here are the 2 output files from running step A of the pipeline previously. For each dataset, we define its name, the input file, and also for each of them we can define 2 optional transformations. The first one is a mapping file for changing the chromosome notations, for example from 1 to CHR1. And the second is a leftover chain file for converting between assemblies. This is necessary to normalize the data before bringing it all together. The pipeline has already completed, and as you can see, the file result B was generated. This is our final product. Now, if we peek inside, we'll see that it contains AC and AN fields summarized from both datasets, without containing any personally identifiable information. Now, of course, AC and AN are not the most exciting statistics, but remember that this is a proof of concept demonstrating some best practices for designing portable federated pipelines. We hope that by adopting these principles, exchange and reuse of genetic data will become a little easier. This repository will continue to be maintained, and everyone is welcome to ask questions, open issues, or contribute code or documentation. Thank you for your time.